Well, hello everyone. Thank you for this opportunity of being here and presenting my work towards fast and accurate phylogeny estimation with self-attention networks. The problem at hand is that of phylogenetic reconstruction, namely given a set of homologous sequences, protein sequences in our case, we want to reconstruct the tree topology which describes their evolution from a common ancestor. One issue that makes this problem hard is the fact that the number of possible unrooted binary tree topologies grows super exponentially with the number of leaves, that is the number of sequences. So for instance, already with 10 leaves, we have more than 1 million possible tree topologies. This entails the fact that state-of-the-art methods for the task as maximum likelihood and Bayesian inference need to explore a huge tree space, which makes them computationally costly. And for the same reason, existing deep learning approaches to the problem, which frame it as a classification problem, are limited to trees with 4 leaves. Another class of methods works rather by computing distances between sequences. Indeed, one can see the branches of a phylogenetic tree as labeled with branch lengths, positive weights, which represent the expected number of substitutions per site in a sequence evolving along that branch. This naturally defines a metric on the set of leaves, with the distance between two of them being given by the cumulative branch length on the path going from one leaf to the other. A distance-based method as neighbor joining is fast and guaranteed to recover the true tree topology given the correct evolutionary distances in input. But how do we compute these distances? Distance estimation is typically performed in the maximum likelihood framework, and for simple enough models of evolution, the maximum likelihood estimate for the evolutionary distance between two sequences is even given by a closed expression. Nevertheless, distance estimation usually only considers two sequences at a time, which leads to worse reconstruction accuracy with respect to a full-scale maximum likelihood approach. Moreover, these distances are not independent. They have to satisfy, for instance, the triangle inequalities, the 4-point conditions, and so on. So the idea is to train a neural network to predict, given an alignment, all the pairwise evolutionary distances, and do so exploiting all the information contained in the input alignment. To do so, we take a supervised learning approach. Namely, we generate random trees and simulate evolution with a probabilistic model along them. And this gives us our training data, which consists then in alignments with the corresponding label being all the pairwise evolutionary distances between the sequences in the alignment. The advantage of such a strategy is the fact that even if estimating the parameters of a complex model of evolution is computationally expensive, sampling from it is typically computationally cheap, so that we can generate as much training data as we need. And moreover, even if the training process may be long, it only needs to be done once, guaranteeing then fast performances at the inference time each time. So here we have an overview of our method. Once properly encoded, an input alignment is processed through several steps. And in the end, we get as an output n choose 2 real numbers, which correspond to the predicted evolutionary distances, which we can then feed into the neighbor joining algorithm to reconstruct a tree. So to feed the data into the neural network, we need a suitable representation. We can use a one-hot encoding to represent an alignment as a 3D matrix, that is a tensor. Namely, representing each character with a vector containing all zeros, but a 1 at the index corresponding to that character. So for instance, here in the figure, A would become 1, 0, 0, 0, C would become 0, 1, 0, 0, and so on. So here, for ease of illustration, I've shown an alphabet with only 4 characters, a nucleotide alphabet. And even though our method could in principle work with the nucleotides, for the moment we only focused our work on protein sequences. So the actual alphabet that we are using is an alphabet with 22 possible characters, one corresponding to each amino acid, one for an undefined amino acid, and one for a gap. After the encoding, we embed each of these vector representations of amino acids into a higher dimensional space, R to the D, with D being 64 in our case. And then we take pairwise averages over the rows to get a representation, to get representations of pairs of sequences, because it's from these representations that we will eventually get the predicted corresponding evolutionary distance. So if in the initial encoding we had the first row representing the first sequence, the second, and so on, now we will have the first row representing the first and second sequence, the second row representing the first and third sequence, and so on. At some point we will have the second and third sequence, etc., in lexicographic order. So these representations of a site in a pair of sequences are those that we will be mainly working with, processing them either independently through position-wise feed-forward layers, namely, again, applying the same linear functions intertwined with non-linearities independently and in the same way to all of these vector representations. Either we will process them, allowing them to interact with each other through a self-attention mechanism. So in the final steps from these tensor representation, we apply a final position-wise fully connected layer with a single output feature, which makes our representation two-dimensional. And finally, we do an average over sites, that is over the columns, to get the final network prediction. So why self-attention? In a nutshell, self-attention is a mechanism that allows to update the vector representations of a set of objects, allowing them in a certain sense to share information among them, and thus resulting in some new context-aware representations. Notably, the mechanism has been introduced in the context of natural language processing, specifically for machine translation, originally, a context in which it allowed to embed the words in a sentence in a context-aware fashion, so that given that the meaning of a word may depend on the context one finds it into, leading to better translation accuracy in that case. So in our case, what we want is to share information among the different pairs in the alignment to improve the final prediction. And another point to put forward is that the same self-attention update can be applied to a set regardless of its cardinal, which allows us to apply the same method, the same trained neural network, to our alignments of arbitrary size, both in the number of sequences and in the sequence length. Because I didn't mention this before, but existing deep learning approaches, as far as we know, not only limit themselves to alignments with only 4 sequences, but also to alignments with a fixed maximum sequence length. So inside these transformer blocks, the attention update is done in 2 steps. Firstly, over columns. That is, for each side, we allow to share information. We allow information to be shared among the vector representations of that side in each pair. So here in the figure, now we're focusing on the first column, the first side. Here we apply the attention mechanism to all the vectors in that column. So these 3 in this case. And analogously, then we process the the representations, applying the self-attention mechanism over rows. For each sequence pair, for each row, we share information among the vector representations of each side in that pair. And in the field of machine learning, it's often desirable for the network's input to be invariant to certain transformations of the input. So, for instance, if we're training a neural network to recognize images of cats, we want it to be able to do so even if we, say, rotate the input image by 90 degrees. And so there's two ways to deal with that, either with data augmentation, so augmenting the training data with various transformations of the inputs, hoping that the network learns to be invariant to them by itself, or more sophisticated way is to encode these possible transformations directly into the network's input, making it structurally invariant, which allows to use less training samples and less parameters. So in our case, what we want, for instance, is that for the output of the method to be invariant to permutations of the input sequences in the alignment. So if we shuffle the sequences in the input alignment, we still want to get the same predicted tree. And given the network architecture, we are guaranteed to do so. Furthermore, the prediction of our network is also invariant to permutations of the columns, that is, permutations of the site. And this allows us to exploit the common assumption in evolution models that evolution is independent and identically distributed at each site. Nevertheless, this doesn't limit the application of our method to evolution models which do model a dependence between sites, because again, we can deal with this just as in regular transformers in natural language processing, a context in which the order of the words in a sentence does matter. There's a way to deal with that, and we can just apply it without having to change our neural network architecture. So we generated several data sets with different sequence simulators. The first one is a Seq-gen, a very popular one, which we use to generate simulations based on the PAM matrix of amino acid substitution. And we trained our Phyloformer model on 100,000 alignments of fixed sequence length and a fixed number of sequences. So we trained our model only on alignments with 20 sequences and 200 sites. But then we tested it on several different datasets with a fixed sequence length and increasing number of sequences, and with fixed number of sequences and increasing sequence length, testing on 150 trees for each combination. So here we can see the results. Here we're plotting in terms of Robinson fold distance, which is a measure of the error between the true and predicted trees. So the lower, the better. We are comparing our method, Phyloformer, against maximum likelihood as implemented in the software IQ3, and against a standard distance-based method, which computes the maximum likelihood estimates of the distances and then uses neighbor joining to reconstruct the tree. And we can see that we get consistently better performances than the standard distance-based method, and performances which are close to maximum likelihood for settings close to the training ones, namely when the number of sequences isn't that much greater than 20. This can be explained by the fact that as the number of leaves increases, so do the evolutionary distances between two randomly picked sequences along the tree. And so these distances at some point start to fall outside the range of distances that the network has seen during training. So we've seen this same trend in the several different simulations, as well in the case of model misspecification. And we're working on making the method scalable to this case as well. Because, okay, I'll talk about this later if someone is interested. Okay, the second simulator we considered is a previously published simulator, which was published along with a simpler neural network architecture, which allows us to also compare our performances to those of a previously published neural network method. So here on the left, we have, again, the Robinson full distances, this time as violin plots between the true and the predicted trees for different methods. Our method, Phyloformer, IT3, maximum parsimony, simple neighbor joining with Hamming distances, and the previously published neural network, DNN3. So this is a complex model employing 9 different matrices of amino acid substitution and modeling heterogeneities both across sites and along branches. And 12 test datasets were generated with different parameters. And to test our model, we trained it only on the easiest parameter configuration, namely the one on which all the methods perform best, the one here in the upper left corner. So for which, as you can see, the Robinson full distances for all methods are quite low. Nevertheless, if you look at the plots, one can see that Phyloformer always manages to output Robinson fold a distribution more skewed towards low Robinson fold values. And moreover, if we just look at the mean Robinson fold distance between the true and predicted trees, we see that we get the best performances across all methods on 9 out of 12 of the 12 datasets, being outperformed in the remaining 3 by not that much, only by maximum likelihood methods, which, as we shall now see, are significantly slower. So in terms of speed, again, we can see the performances of the 3 considered methods for the time simulations plotted on a log scale. So we have maximum likelihood, Phyloformer, and a standard distance-based method, both for increasing number of leads and increasing number of sites. And again, this is on a log scale. So here it's easy to see, distinguish the different methods, but maybe it's more intuitive on a normal scale. And one point to put forward here is that we are processing one alignment at a time for this plot that is using a batch size of 1 as input to our neural network. Nevertheless, the method is actually highly parallelizable, and we could process several trees at once, several alignments at once, obtaining even faster performances, with the only constraint being given by the available memory. Future work will include training the model on a more diverse dataset in terms of number of sequences and of branch length distributions. Train the model on more complex models of evolution, which could result in a greater foothold against the maximum likelihood method, as maximum likelihood makes a lot of simplifying assumptions as in the independence between sites to perform the likelihood computations, so that the full likelihood can be written as the product of the single likelihoods for each site. Whereas our method is not constrained by the complexity of the evolution model. Then we will explore the performances of our network combined with different clustering algorithms other than neighbor joining, introduce a measure of uncertainty in the predictions, and further improve scalability. The work, a preprint of this work is available on bioRxiv for those who might be interested. And I'm also giving a poster presentations. So if you're like to discuss, come talk to me, write me a message, a mail, whatever. I would be happy to discuss this. And I like to thank for their contribution, Dexian Chen, Martin Raffel, Johanna Trost, and Philippe Weber. And thank you for your attention. Okay. Okay, I think I can't hear you. Okay.
Okay, nice talk. And any question? Actually, we can have just one, maybe. We run out of time. Yes, it's just one.
Okay, I think mine is pretty quick, which is
two quick questions.
that you include the gap character in there, which is intrinsically a potential violation of the IID assumption. I'm curious, when you did your simulations for training, did you...
Okay. Sorry, I'm gonna stop you right there because so actually we did include a gap in the possible encoding, but for the moment we didn't consider evolution simulators with gaps. So it's our method is ready to work with gaps, but we haven't done it yet. But so I'm interested in your point because that's something that we'll do.
Okay, well, thank you, and it was a wonderful talk.
Okay. Thank you.
Hi, also just quick. There's work on parameterized inference within simulation models that you might be able to take advantage of to set the parameters of the evolutionary model that you're using to train your model. Because presumably you want the parameters of those evolutionary models to best match the realistic data. Real life.
Yes, exactly. So this is the work of my first year of PhD, and the project also includes in the future to try and develop a more realistic sequence simulator, trying to use an adversarial approach, something like train our model on more realistic simulations and make it more performant on real data.